the examples of the Bravais lattice in 3 dimensions. So last time I mentioned the cubic lattice, Bravais lattice, the tetragonal Bravais lattice, and the orthorhombic Bravais lattice. So now the next one is the hexagonal lattice. So the hexagonal Bravais lattice is defined by 2 primitive vectors, A1 and A2 having the same length, and third one that is orthogonal, and these two, A1 and A2, having an angle of 60 degrees. So the angle between A1 and A2 is 60 degrees, and the angle between A2 and A3 and the angle between A1 and A3 is 90 degrees. So the hexagonal Bravais lattice has a vector A1 like this, a vector A2 that has the same length, and here there is an angle of 60 degrees, and then the third vector is perpendicular to the plane of these 2 vectors. So A3 is here and has an angle of 90 degrees with A1 and an angle of 90 degrees with A2. So this is the hexagonal Bravais lattice. So if I have an hexagonal Bravais lattice and I look in the plane here, perpendicular to A3, in the A1-A2 plane, I will see, so this is a 2-dimensional system, and in this plane, A1 and A2 plane, I will have my angle, my vector A1 here, my vector A2 here, and the lattice of points that I will see in 2 dimension would be something like this. So these are points of this lattice. Then I have another point here, and then I have another point here. So this would be, for instance, minus A2 plus A1, and so on. So this is, and from here I can have minus this vector going here, and so on. So this is the lattice that I have in 2 dimensions, and this is also a Bravais lattice, and it's called the triangular lattice. So in 2 dimensions, the Bravais lattice that is defined by 2 vectors of the same length and with an angle of 60 degrees is called the triangular lattice. Yes?
For the hexagonal lattice,
Yes.
how does the norm of A3 relate to A1 and A2? Does it differ?
E3 it can be different, yes. Only the length of A2 and A1 has to be the same. Okay, so now going down in symmetry with less restriction, I can define also the monoclinic lattice. The monoclinic Bravais lattice, and this has as constraint just the angle between A1 and A3 and the angle between A2 and A3 is equal to 90 degrees. So one has just the third vector perpendicular to the other two vectors in the monoclinic lattice. So one has A1, then my angle here and length I can choose as I want, A2, some angle here, and then A3 is perpendicular to the other two vectors, so to A1 and to A2. So this is the monoclinic lattice. And finally, the last one that has no restriction is called the triclinic lattice.
Excuse me. So is it like the hexagonal is also on the plane?
The hexagonal is a special case of the monoclinic. So the triclinic has no restriction. No symmetry. So I have a vector A1, I can choose a given length. A2 has a length and an angle which can be anything, and A3 has also a length and an angles to the other vector which can be anything. So this is called the triclinic lattice. So these are classes of Bravais lattices in 3 dimensions. We've also introduced for 2 dimensions another Bravais lattice which has some high symmetry, which is the triangular lattice. Okay, so this is for the classes of Bravais lattices. And now I would like to tell you about 2 special lattices, special in the sense that they are common in nature. So these 2 lattices are the BCC, body-centered cubic lattice, and the FCC, face-centered cubic lattice. So, an example of common lattices in nature. So, one of them is the body-centered cubic lattice. BCC, body-centered cubic lattice. So this lattice is defined as a cubic lattice with 2 atoms in the basis. So I have a cube here. With the 3 primitive vectors A1, A2, and A3 corresponding to the edge of my cube, and in the cubic-centered, body-centered cubic lattice, I have lattice points at the corners of the cube. And I have also lattice point at the center of the cube. So I defined the body-centered cubic lattice as a cubic lattice with 2 atoms in the basis. And the positions of these 2 atoms, their D vectors are D1, just 0, 0, 0, and D2 is just the center of the cube. So if my lattice parameter here is A of my cubic lattice, D2 is A over 2, A over 2, A over 2. So the BCC lattice is a cubic lattice, and in addition, at the center of each cube, I have another lattice point. So this is the body center cubic lattice. And it is a lattice that is common in nature, in particular for metal. For instance, iron, chromium, molybdenum, and tungsten are crystallizing in this structure, in the body-centered cubic lattice. So iron, for instance, is like this. Has this crystalline structure. So now I defined this body-centered cubic lattice as a cubic lattice with 2 atoms in the basis. So this is a crystal structure. Now, is it also a Bravais lattice? Can one find 3 vectors, A1, A2, and A3, that map, give rise to the full points of in this lattice by N1, A1, plus N2, A2, plus N3, A3. I've got another one here. No? Yes? Yes. Yeah. It is also a Bravais lattice.
Extend it to some few other cubes, and like extend this figure to few other cubes and include the centered.
I mean, the Bravais lattice, the body-centered cubic lattice in space is this translated to infinity, and this gives the lattice. So I defined it as a cubic lattice, that is a lattice that would have, for instance, the primitive vector A1, A2, and A3, the conventional primitive lattice vector of the cubic lattice. And I considered two atoms in the basis to define it. So one atom here and one atom here with these two vectors. So at the moment it's defined as a crystal structure to show that it's a Bravais lattice one needs to find three vectors that would directly give the full lattice without need of two atoms in the basis, just one.
For me, I'm not seeing those because I'm seeing if you use the vertical as maybe A3 and then the other, the ones in the XY plane would be A1 and A2. I don't see how you get the one at the center.
That's because you are choosing the wrong base.
Yeah, so basically one needs to find vectors that don't have this orthogonal arrangement, and that a possible choice would be, for instance, A1. One keeps the same A1 and A2. So, and A3 would be this vector. So if one does that, actually one can generate the full lattice. All the points can be reached by n1 a1 plus n2 a2 plus n3 a3. So for instance, this point obviously is 1 times a1 plus 1 times a2, 0 times a3. This point would just be 2 times a3, so 0, 0, 2. This point would just be this one minus a2, so this point would be just 0, minus 1, 2. I can reach it by going first here, so 2 times a3, and then I come back with minus a2. I reach this point. Then to reach this point, for instance, I go from here with minus a1, so minus 1, 0, 2. And to reach this point, I just subtract also a2, so minus 1, minus 1, 2, and so on. So I can reach all points. And for instance, this point, which would be in the next cube, that would be just at the same height than this one in the next cell at the center. How would I get it?
You think how to use the 3?
I would have just A3 and add A1. So basically I'm reaching all points in the of this lattice. So it is a Bravais lattice. The body center cubic lattice is a Bravais lattice. BCC is a Bravais lattice. Okay? You all agree?
Yes.
And then there is another one that is also common in nature, that is also of cubic type, which is the FCC, face-centered cubic lattice. centered. FCC, which is also a Bravais lattice. The face-centered cubic is just obtained by considering a cubic lattice and points on each face of the cube. I will come back to this lattice a little bit later and define it, discuss it, but I just wanted to mention here that there is another also common Bravais lattice that is called the face-centered cubic lattice. And for instance, aluminum, silver, gold crystallize in the face-centered cubic lattice. So this is also a common lattice in nature, in particular for metals. Okay, so this was to give examples of Bravais lattices. And now I would like to introduce the notion of packing. Packing of spheres, which is also useful to describe crystal structure. So the next item is packing. And by packing, I mean packing of spheres. And the idea is that to some first order approximation, atoms may be considered as just spheres. And one would like to ask the question, what is the most efficient way in 3 dimensions to pack these spheres? That is, to have the least amount of empty space between the sphere. So this is the idea one would like to know for Bravais lattices. What if I have, I consider the point of my Bravais lattice as corresponding to the position of atoms of sphere? What is the most efficient packing of this sphere? Which Bravais lattice gives the most efficient packing, for instance? Okay, but let's first consider packing in 2 dimensions. So I imagine that I have spheres, balloons, on the floor, and I would like to know what is the most efficient way to pack them, to have the least amount of space between the spheres, or just disk. And I want to know what is the best way to arrange them to have the least amount of empty space when they touch each other. So first let's look in plane in 2 dimensions. So if I have spheres of diameter A, or disks of diameter A, I'm just looking from the top. If I want to pack them in the most efficient way, okay, I arrange them so they touch each other. And then for the next row, I would put them just here where there is some space. So I would put them here, 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 here. Okay, and then I will continue like this. Touching it down. So in 2 dimensions with disk, one can show that this is actually the most efficient way to pack the disks. Then this corresponds to a triangular lattice. My disks are centered, the center of my disks are positioned on a triangular lattice. Clearly, if I do something like this, with the same spheres or same disks, I pack them on top, well, I meant on a square lattice. The packing is less efficient. I leave more space, and the efficiency of the packing, one can actually quantify it by a packing fraction. So the packing fraction for the lattice, if I consider I will define it for 3 dimensions, but 2 dimensions just, I will define it for 2 dimensions, but for 3 dimensions it's the same idea. So the packing fraction is defined in my case here as the surface of the disks, the projections of the sphere. So the surface occupied by a disk and divided by the total surface per atom. So this will be just the surface of my disk divided by the total surface per atom or per disk. So the surface occupied by the disk or by an atom is just pi A over 2, the diameter square. So this is the surface occupied by my atom, and the total surface per atom differ in the cubic, in the square and triangular lattice. So the total surface per atom in the triangular lattice is just the surface of this diamond, or this length, which is A times this height, which is square root of 3 divided by 2A, because from Pythagoras one can get this height. So in the triangular lattice, the total surface per atom is A times square root of 3 over 2A. So this is for the triangular lattice. And if I calculate the surface per atom, in the case of the square lattice, it's just A squared. So for the square lattice, it is just okay. Is it clear? So I just calculate the surface per atom, which corresponds in this case just to the surface of this object here, which includes full atoms by putting the pieces together. So this surface is just A times square root of 3 over 2 times A. And here this is just the surface of my square here. So if I calculate now the packing fraction for these two types of arrangement of the spheres, disks, I obtain for the triangular lattice as packing fraction this divided by this, which gives me pi over 2 square root of 3. And for the square lattice, it's the same thing divided by A square, which is just pi over 4. So from here, one sees that this is larger than this. That is, the packing of the triangular lattice is larger than the packing of the square lattice. Okay? So it's a quantitative measure of the packing, and indeed the triangular lattice has a better packing, gives rise to a better packing of this than the square lattice. And actually, it is the best way in 2 dimension to pack disk, the triangular lattice. Okay, so this was in 2 dimension. One can, of course, extend it to 3 dimension. The volume of the sphere divided by the total volume per sphere or per atom for the packing in 3 dimensions. So now we continue in 3 dimensions. And actually, we want to optimize the packing of the spheres. So if I start from the spheres on the ground, on the floor, packed in this triangular lattice, then seeing from the top, I would have this kind of layer of spheres. So this was what I had before for my first layer of spheres on the ground. So this is a triangular lattice. So I have my first layers of sphere on the ground. And now, if I want to put second layers of sphere, it is clear that the best way to optimize the packing is to place my sphere on the empty space here between the spheres of the layer below. So, for instance, I can center my spheres of the second layer with points here. So this would be like this. This would be the second layer. So the next one would be centered here. Okay, and then the layer, the row, the continuation would be here. Here. Touch. Things. So no, I forgot one. Sorry. Here. Here below. So. Okay, so the second layer is also a triangular lattice, and it's centered on these holes, the red holes here. maybe it's a bit more clear if I do this. So this was my starting triangular lattice. So my first layer of spheres were centered on these sides here of the triangular lattice, which I will call A sides. So this corresponds to the A side, the first layer of spheres. And the second layer of spheres, I centered it on these red sides, which I will call B sides. So if you want, where's the mic? I have initially this triangular lattice, and I have centered the atom of the second layer at the center of these triangles, which are the triangular with the corner or the edge on top here. That is, if you want, I have an up triangle, a down triangle with nothing, an up triangle and a down triangle with nothing. So in this triangular lattice, I'm occupying the center with a spheres in red of one out of two of the empty sides. You see it? Okay. This triangular lattice, which corresponds to the center of the first layer of spheres, has, if one draws the triangle of the lattice, has all the sides in red here occupied, and all these sides here, which are at the center of the downward triangle, empty. And again, the next field and the next one empty. So in my triangular lattice here, I have two types of empty sides. The red ones, which are called B, and there are also the green ones, which I will call C. I can continue here. I have other C sides. So basically I have A sides, B side, C sides, A side, B side, C sides. And the second layer, I centered my spheres on the B sides. But actually, I could, for the second layer, as well have chosen the C sides. And it would give me also a triangular lattice, because of course the red sides form a triangular lattice that is has the same lattice parameter than the A sides. Just the same type of layer, just shifted laterally by this amount. I could have chosen instead the C side, which would also form a triangular lattice, which would be exactly the equivalent to the red arrangement, would give me a packing that is as good as the red one for the second layer. You agree? It's okay? Okay, so actually for the second layer of spheres, I have two possibilities, B or C, which give the same good packing, optimal packing for the arrangement of my spheres. So then one can continue in the sense, if I want to optimize the packing when I put my layers of spheres, I have initially the A stacking of my spheres. For the second layer, I could choose, for instance, B, the B type of packing, so the red one. And the third one, I could choose C. And then I could start again with A, B, C, and I would obtain a very good packing of my spheres, a very good packing fraction. Now, I could as well decide to take A, and then C, and then B. It would give me the same good packing. So I have several choices, and they all give the same packing fraction. I could also do just AB, AB, AB. This would be fine too. I would have also the same type of same packing fraction. So basically, there are several possibilities to obtain the best packing, and the algorithm is if the first layer is of the A type, so my white arrangement, the white triangular lattice. The second layer must be different. It must not be A, it can be either B or C. So it must be different from A because that's a poor packing. So it should be either B or C, and this is equivalent. So this is for the second layer. Now, if my second layer is B, if I have chosen to pack after my A layer the second layer on the B sides, so if the second layer is B, then the third layer must be either C or A. And so on. So basically, I can generate sequences of packing that all have the same efficiency, and where just if I choose A packing for the first layer, the second has to be different, so either B or C. Then when I have the second layer, the third must be different, so if it's B, it must be either C or A, and so on. So I can generate an infinite sequence, or infinite, I have a variety of choices for packing spheres the most efficient possible way. And one example is, for instance, these sequences could be A, and the next one must be different, so it could be B, and C, then A, B, A, C, have a wide choice, and it doesn't necessarily need to be periodic, so I have a lot of choices. So this scheme yields the most efficient packing in 3D. This is a hand-waving argument, but it holds. This is the most efficient packing in 3D. Now, of course, if one talks about crystals, one needs periodicity. So one can only consider the sequences that have periodicity in this arrangement. So for crystal structure, one needs a periodic sequence. Or a sequence. So, for instance, the simplest could be A, B, A, B, A, B, and so on. And this actually corresponds to what is called the hexagonal closed packing, HCP. So it gives rise to the hexagonal closed packed structure, HCP. And a number of metals have this type of structure, hexagonal closed packed, and in particular magnesium. However, this sequence, ABAB, of the packing there is not a Bravais lattice. And one can see it actually immediately, because if I have only the AB packing, okay, as Bravais lattice vector, I will have in particular the difference between the B and A, the vector that brings from A to B, because these are two lattice points, so the difference is also a lattice vector. But this vector, if I continue it, the projection of 2 times the vector AB will bring me here on the empty side, the C side, and the C side is not included in the AB sequence. So I end up on a point which is empty. So if this was a Bravais lattice, I would have also a point here, which I don't have, so it's not a Bravais lattice. So the hexagonal closed packed structure or lattice is not a Bravais lattice, but it exists in nature. With 2 atoms in the basis. So this sequence is actually not a Bravais lattice. Instead, the other sequence, the simplest, which is ABC, ABC, is a Bravais lattice. So I have to erase this. Well, okay. Maybe I leave it. So I'm continuing here. The sequence A, B, C, A, B, C, which gives very good packing, closely packed structure, is actually the face-centered cubic structure. So ABC, this packing of seal corresponds to the face-centered cubic lattice. So the FCC lattice that I mentioned before, and this is actually the most efficient way to pack, one of the most efficient way to pack spheres, the face-centered cubic structure. So it's not obvious, but I will show you that this is reasonable, that this stacking ABC corresponds indeed to the face-centered cubic lattice. So now I will spend a little bit of time on the face-centered cubic structure and the lattice. Okay, so the face-centered cubic lattice, to describe it, it's a cubic lattice with 4 atoms in the basis. This is the conventional way to describe it. So I have a cubic lattice and cube. Okay, so the first description of the face-centered cubic lattice is that it's a cubic Bravais lattice with a basis of 4 atoms. So it is a cubic Bravais lattice, so I have atoms on lattice point at the corner of the cube, and the second, the other atoms are placed on the faces of the cube in the FCC structure. So I have one atom which is here, one atom which is on this face here. Here I have one atom that is on the front face here. I have one atom, so these are the 3 faces that one sees. And the back Okay, and the faces, the base face here has also an atom here. This back face here has an atom here, and the face in the back there is also an atom. So the atoms one sees, and this one, this one, this one. And then on the top face, on the side face here, and on the front face here, and the other atoms are in the back. Okay, so this is my cube with the atoms on the corner and faces. And in this description of the face-centered cubic lattice, I have a basis with 4 atoms whose vectors are d1 is at the origin. So my cube has spacing a lattice parameter A here, this length, the edge, the side of the cube. So the first vector gives this atom, d equal 0, 0, 0, d2. The second atom is at A over 2, A over 2, 0. So the D2, this is the atom number 2 here. And the atom number 3 would be 0, A over 2, A over 2. So this is so this would be the atom number 2. This is the atom number 3. Outside. 3. This is 1. And the atom number 4 would be A over 2, 0, A over 2. So this is the atom 4 here on the front face. So these are this is the conventional description of the FCC lattice. I have a cubic lattice, so with basis primitive vectors A1, A2, A3, and I have 4 atoms in the basis, this one, this one, this one, this one, with these vectors given here. So with this, I generate the full crystal structure. This atom is just given by this one plus the vector here. It would be E1. One can see that one obtains all the atoms. One can join all the atoms in the crystal structure with A1, A2, and A3, and these 4 vectors as a crystal structure. Now, so this is the conventional or the first description of the FCC lattice. And the second one is as a Bravais lattice. So with just 3 vectors that generate the full lattice of points of the FCC lattice. And so the second description that shows that it's a Bravais lattice. So it's just the Bravais lattice, FCC Bravais lattice, with as primitive vector, for instance, A1 is equal to D2, A2 is equal to D3, and A3 is equal to D4. So with this choice of primitive vector, I generate all the structure, all the FCC lattice. So here A1 would be D2, that is this vector. This would be A1. A2 would be D3, this vector. So this would be D2. And A3 would be D4, so it would be this vector. So with these three vectors, I can show that all points in the FCC lattice are reached by N1, A1 plus N2, A2 plus N3, A3. It's, well, it can be shown
Excuse me, madam.
Yes?
I thought that since A2, that atom in the XY plane at the
Yes.
center,
Yes.
that the center of the diagonal of the square, then it wouldn't be A out of 2, but instead A out of 2.
Sorry, you mean this atom?
Yes,
D2?
yes, yes, yes.
It's
If
at the center of the face,
Yes.
so its coordinate are
So it is at the
half
center
of that and half of that. Okay, this
I
would
thought
be
it is at the
X,
center of
this
the
would
diagonal.
be center of the diagonal. The length of this is the square root of 2 divided by 2a. But the coordinates are a over 2 times a1 plus, sorry, this one, plus a over 2 times a2. Or, I mean, in x,
The
yeah.
cubic.
Oh, okay.
Okay, so the way to show that all atoms are reached, so with these three vectors, I generate, of course, I have the atom at the origin. I generate this vector, these atoms, and this atom with just N1, N2, and N3 equal to 0. I already obtain with, with these primitive vectors, I obtain directly the position of this atom, this atom, this atom, and the one at the origin, so the point in red are immediately obtained. And then to show that one can obtain all other atoms, it's enough if I show that by linear combination of these three vectors, I can generate the primitive vector of the cubic cell. If I show this, then it's obvious that I can reach all of the atoms. And this is indeed the case. That is from sums and differences of these three vectors, A1, A2, and A3. I can obtain the primitive vectors of the cubic Bravais lattice, the cubic lattice, A1 cubic, A2 cubic, A3 cubic. So, for instance, well, A1 cubic, that is the vector that would go from here to here, I can obtain it just as A1 plus A3 minus A2. So if I do A1, which is this vector, plus A3, which is this vector, minus A2, which is this vector, I obtain A, 0, 0, so I obtain indeed the primitive vector of the cubic lattice. The A2 of the cubic lattice is obtained as A1 plus A2 minus A3. If I do A1 plus A2, so A1 plus A2 minus A3, I obtain 0, A, 0, and I obtain the edge, the vector at the edge of the cubic lattice here, A2 cubic, and the third one is obtained similarly as A2 plus A3 minus A1. So if I do A2 plus A3 minus A1, I obtain 0, 0, and A. So I indeed obtain my three primitive vector of the cubic lattice, and given that, it's clear that starting from these four atoms, I can obtain all atoms in my FCC lattice. So it is indeed a Bravais lattice, and for instance, the primitive vectors could be these three vectors. Okay, so this generates all points in my Bravais lattice. So red points with I get all the points in my FCC lattice. Okay, so this was to show that this is indeed a Bravais lattice, the FCC lattice, and now to see that it is the kind of packing I mentioned, ABC, ABC, one has to look from the diagonal of the cube. So if I look from the diagonal of the cube, so this would be along this kind of axis. The planes of atoms that are present are a plane that would be here, so perpendicular to this axis of the diagonal of the cube. Then I have another plane that essentially includes these three atoms, and in the back these three and this. So this plane, which is perpendicular to the diagonal of the cube, includes these atoms that are on a triangle here. And here I have another plane of atoms that includes that goes through the diagonal of the face here, the diagonal of the face here, and in the back of the cube on the diagonal of the face here. So I have another layer of atoms, and these atoms actually form triangle. So basically, from the diagonal of the cube, perpendicular, I have these planes, and this would correspond to the plane with the atom in the A stacking. This would correspond to the plane with the atom in the B stacking, and this would correspond to the plane with the atoms in the C stacking, and then I go back again to the A stacking. So this is the correspondence between the cubic FCC lattice and the hexagonal ABC packed structure that I mentioned. It's not easy to see, but you just need to know it, and it's reasonable that this close-packed ABC indeed corresponds to the FCC structure. Just to finish this, so if one looks from along the diagonal of the cube, so that is along, which would correspond to the hexagonal C-axis. I call it C because it's different from the A and B axis. C would correspond, in what I mentioned previously, for the hexagonal structure to the A3 axis. But since it has a length different from the other two hexagonal vector, A1 and A2, its length would be C, and we call it the C-axis also. So along the diagonal of the cube, which I call the C-axis, one would see triangular lattices. So this would correspond to, these points would correspond to the A point, and this would be the vector perpendicular to the blackboard would be the C-axis. So I would have a triangular lattice like this. With here the projection of the atoms on the A sides. Those on the B side would be like here. And those on the C side would be here. That is what one would see from the diagonal of the cube for the projection of the atoms on the black box plane. Okay, this is just to tell you what is the correspondence. Okay, at least it sounds reasonable that there is this, that the ABC packing is actually the FCC, corresponds to the FCC Bravais lattice. Okay, so now I want to introduce some other measure related to crystal Bravais lattices, which is the coordination number. So I will erase this. Okay, so something that is also useful for Bravais lattices are the coordination numbers. So the coordination number of a lattice point in a Bravais lattice. And this is the number of nearest neighbor points. Or the number of nearest neighbors to a given lattice point. So let's first look at the simple cubic lattice. So I have my cube with lattice points here. Okay, I have other cells on the sides, below, and yeah, I have many other cells. So let's consider a point in the simple cubic lattice. How many nearest neighbors does this point or atom have?
6.
6, yeah. So the coordination number is 6. Each point has 6 nearest neighbors at distance A. So 6 nearest neighbor at distance A. And just to continue, how many second nearest neighbor would each point have?
4.
So the second nearest neighbor are along the face diagonal of the cube. So one has 4 in the horizontal plane, 4 in one of the vertical planes, and 4 in the other vertical plane, so one would have 12 second nearest neighbor. 12 second nearest neighbor, and they are at distance square root of 2 times A. And just to finish, how many third nearest neighbor, that is the points that would be along the diagonal of the cube?
8.
8 third nearest neighbor. And this is at square root of 3A. Okay, so this is for the simple cubic lattice. Now, BCC lattice. So, in the BCC lattice, I have points at the corner of my cube, and I have a point at the center of the cube. So if I consider a point of my lattice, for instance, at the center of the cube, how many first nearest neighbor do I have?
8.
Yes, 8. So the coordination number is 8. 8 nearest neighbor. And this is at a distance square root of 3 over 2A. And how many second nearest neighbors?
6.
6. This would be the one at the center of the next cube. So 6 second nearest neighbor, and they would be at a distance A. Okay, and finally the FCC, base center cubic. So this one has points here at the edges, at the corners of the cube, and then on each facet face of the cube. So, okay, if I consider a point for instance, that one at the corner of my cube, how many first nearest neighbor does this point have? So the first nearest neighbor would be at the center of the faces. So I would have 4 in the horizontal plane, 4 in one of the vertical plane, and 4 in the other vertical plane, so 12. So 12 nearest neighbors at the distance square root of 2 over 2A. So this is for the first nearest neighbor. And how many second nearest neighbors?
6.
6. This would be just the one that are along the edge of the cube. So 6 second nearest neighbor at A. So, to summarize, the FCC has the largest coordination number, 12, number of nearest neighbors, which also is consistent with the fact that it's the most highly packed structure. So FCC has 12. So FCC has the largest number of nearest neighbors, 12. BCC has the second largest, number of nearest neighbors, 8. And simple cubic has the third largest, that is 6. So as homework, I will ask you to calculate the packing fraction of these 3 Bravais lattices. So calculate the packing fraction of the FCC, BCC, and simple cubic lattice. Each of these lattices. And one hope, well, you should get FCC highest, BCC second highest, and simple cubic the least in this, also for the packing fraction. Okay, so I will stop here. Any question? Everything clear? Okay.